In this video, I'm going to begin with defining the first law of thermodynamics. So we know that in this chapter, we're referring to thermochemistry and the energy related in chemical reactions and heat transfer and phase change. So let's define this first law here as that energy is neither created nor destroyed. We talked about how it can be transferred. We also want to add that the total energy of the universe is constant. So that implies that if a system loses energy, it must be gained by the surroundings. And if you recall, the system plus the surroundings together will equal the entire universe. So that's how this law kind of encompasses all of that. So we can see over here in this graphic that we have the internal energy of our system here, and this is indicated over here. So this is the value that we begin with. So if we were to lose energy in our system, our final energy would be down here. And we would say that energy was lost to the surroundings, and the delta E of our system, always reference the system, would be negative. On the contrary, we start at the same point here, the initial energy, the initial state of our system. There's a gain of energy by the system. So now our final energy is up here. And we would say that energy is gained from the surroundings. So the internal energy of our system has increased. And again, referencing the system, our delta E is positive. Our change in energy would be positive. So the internal energy that's referenced here, this is the total energy stored inside of a system. This consists of the kinetic energy, the potential energy, all the types of energy. And by definition, the change in internal energy is going to be given by this equation here, the final minus the initial. We can look at this in a graphic over here that we have H2 gas and O2 gas. They are in a high initial state up here of energy, so their internal energy is high. And then we see a negative change in internal energy when we produce our product here, our liquid water. So just in general, a gas is going to be higher energy than a liquid. So we can see, we can kind of guess and approximate that this is going to be a negative change in energy, in internal energy of our system. So let's continue here and let's further define when we have a positive or negative change in energy. This can be referred to through these specific terms here, where an endothermic reaction, this is going to be a positive delta E, so an increase in the internal energy of our system, where we absorb energy from surroundings. And then here, an exothermic reaction, we're going to say that's a negative change in energy, where energy is released from the system to the surroundings. And when we have this energy exchange between the system and the surroundings, it's going to be exchanged as either heat or work. So these are the only two ways that we can exchange between the system and the surroundings. And we can quantify this change in internal energy as the sum of the Q, so the heat difference, whether it's positive or negative. We'll talk about those implications, and then the work, whether it's positive or negative. So when we talk about Q specifically, this top line here, when our system gains heat, that's going to be a positive Q. And then when our system loses heat, we would say that's a negative Q. Same thing with W here. We always reference our system. So when work is done on our system, that's going to be positive W. When work is done by the system, it's losing energy. So, right, we'll have a negative W. The delta E then is going to be positive if we have a net gain of energy. So the sum of both Q and W. and then a net loss would be negative. So let's see if we can put our skills to the test here in sample exercise 1, where we're asked to calculate the internal energy for a process in which, in part A, our system absorbs 140 joules of heat from the surroundings and does 85 joules of work on the surroundings. So let's see if we can solve for delta E, and we know that that's going to be Q plus W. And our heat here, this is our Q, and work is our W. So it absorbs heat, so that's going to be a positive Q. So I'm going to write 140 joules plus. Now the work is being done by the system on the surroundings, so that's going to be a negative value for my work, so negative W, and I'm going to plug in negative 85 joules. So now I add these terms together. So 140 minus 85 will give me 55 joules. And that's my delta E, my change in internal energy of my system. Let's take a look at example B here. Now my system gives off 22 joules of heat, so that's a negative Q. So we'll plug in that we have negative 22 joules plus my work. That's going to be does 25 joules of work on the surroundings. So that's also going to be negative. So I have 22 and 45, both negative terms. That's going to be negative 67 joules. And in this last scenario here, we're going to see that my system will absorb, so positive Q, 61 joules of heat from the surroundings, and the surroundings do 25 joules, so positive W. So our internal energy change here is going to be 61 joules plus 25 joules, and we get positive 86 joules. So if we were to determine if these are endothermic or exothermic processes, we could say this one is endothermic because it's positive. This one is exothermic because it's negative. And then in this last case here, this would also be an endothermic process. So the last thing that we'll talk about in this video is something referred to as a state function. And by definition, a state function depends only on the present state of the system. So it does not matter the path that the system took to reach that state. For example, there's always some discussion of elevation. So here's this mountain that we're climbing. So whether I took this path like that to reach the top or whether I took a more direct path, this state function of my altitude does not matter what path I took to get to this height up top here, or rather up top here. So enthalpy is a state function, internal energy that we've just defined. Some other state functions, temperature, pressure, and volume, do not depend on the pathway. We can see some examples given graphically here. So this 25 grams of water is at room temperature here. So it doesn't matter if the water was initially steam and condensed and the internal energy lowered, or if it was frozen and melted. Either way, we get to this final state in the middle. And that's what's discussed over here. So Q and W, these are not going to be state functions, although together they do sum to give the internal energy change. So we should note that Q and W do depend on the pathway, but our change in internal energy does not. And we'll continue with a discussion of enthalpy in the next video.